Okay, good afternoon again. It looks like we're right at the top of the hour, so we're going to go ahead and get things started. First off, my name's Tiffany Westpay. I'm the Membership Director here at America Makes, and thank you to each of you that took the time to call in this afternoon. A little bit of information, just briefly about our webinar series before we go any further. We created this about 2 years ago now as an effort to support our mission here at America Makes to continue advancing the technology, but in doing so, increasing the dissemination of information to the membership and to the additive community abroad. So we are hopeful that this will serve as an educational session for you and a resource for your organization. At the end of the webinar, we will have a live Q&A session. So in the bottom right-hand corner of your screen, you'll see a Q&A box. If during the presentation you guys have a question, feel free to type it into that box, and then at the end of our session today, I'll be sure to get that over to our speaker so we can have those answered for you. Now, jumping right into things, today our speaker is Martin Lalou from GranuTools. Martin is an industrial engineer with an MBA. He has a unique background which encompasses technology and business. He's an additive manufacturing enthusiast with a goal to bring market devices to help the technology to have a brighter future. With that, it's my pleasure to hand it over to Martin.
Hi, Tiffany. Thank you for introducing, and hello, everybody. It's a pleasure to meet you today. The TRX webinar. So, as you can see, I will present today a paper written by McGill University and the University of Liège. So it's a collaboration between those two universities. It is on the thermal degradation of metallic powders and the impact on the three key parameters: the spreadability, the electrostatic, and the packing dynamics. So for this study, we use a couple of instruments in order to correlate the measurements with what is happening in the process. The stress state and the flow field of the powder should be comparable in the measurement cell and in the process. So this is why we use an approach. So we studied the macroscopic properties of a powder, so the cohesive index, the density fluctuation, triboelectricity, and we relate those macroscopic properties to the interaction between the grains, so the contact forces, capillary bridges, van der Waals, and so on. As I said, we use the geometry to be close of the application. So here, the powder bed fusion. So to summarize again, we studied the collective behavior and the interaction between the particles, so the forces acting on the grains, contact forces, van der Waals, capillary, electrostatic, and so on. And we relate those properties to the microscopic properties, so the PSD, shape, physico-chem properties, and so on. So to show you today, we are focusing on the powder bed fusion process. So we will study the spreadability, packing dynamic, and electrostatic. So those are the three key parameters in terms of powder characterization we studied. So those parameters drive the process. So spreadability is the homogeneity and smoothness of the powder then after recoater operation. So this parameter is essential because a smooth surface is easier to print, and gives better parts. This parameter will be investigated using the rotating drum principle. So the second parameter is the packing dynamic. This second parameter is a key parameter also because the powder with a fast packing means a part with low porosity. And finally, the electrostatic will be studied also. This is the ability of a powder to create electrostatic charge during a flow. The presence of electrostatic charge in the powder induces cohesive forces leading to the formation of agglomerates. So the project framework in this study, we wanted to monitor thermal degradation with 4 different powders, so 3 different aluminum alloys and 1 stainless steel powder. So we measured those powders at different states. So first virgin powder and then processed powder at different temperatures. So if some people were in a hurry, they have the whole picture here. But then I will show you how we arrive at those conclusions. So working at high temperatures improves spreadability and packing dynamics, and thermal stress can have a big influence on the electrostatic. So here are the 4 powders we studied, 3 aluminum alloys, so A, B, and C samples with different D50, so the A powders, A sample as the lowest, the finest particle, then the B, then the C, and we have a stainless steel powder. So to go through the first parameter we studied, the spreadability. The definition is the spreadability is driven by the contact forces, van der Waals, capillary bridges, and electrostatic. This is the relation between the powder bed and the surface, and it has a big influence on the printability. So here you can see on the right the A image is a powder with a bad spreadability, and the B image is the powder with a homogeneous powder layer, so a good spreadability. So here again, show you a video of a powder with a good flowability. So low cohesion, the particles are rolling on top of each other, so it will be easy to spread. And this powder, it's difficult to break the interaction between particles. You have a lot of fluctuation of the interface, so it will be difficult to spread. So to show you the assessment method we use here, the GranuDrum instrument. The description of this instrument is we use the rotating drum principle. We will rotate at different speeds from 2 to 60, 70 RPMs, and we take a look at the fluctuation of the interface of the powder bed. So for each speed, we take 50 snapshots, we stack them, and we take a look at the average position and the fluctuation of the interface. So to summarize, low fluctuation, low cohesion, so good spreadability. More you increase the fluctuation, more you increase the interaction between the particles, the spreadability will decrease. To show you in this study the device we use, this is the GranuDrum instrument. This is this box. We pour the powder in this cell, so roughly 50 ml, and then we close it up. After that, we measure the virgin powder in this cell, and also we can heat that cell up to 200 degrees. So we put the cell into the machine. So on the left, you have a camera. On the right, you have a wide screen to increase the accuracy of the camera, and then it starts rotating on 2 to 70 RPM. Here it's 60, but we went up to 70, and we took a look at the fluctuation of the powder bed. Here you have low fluctuation, so the cohesive index is low, so the spreadability will be good in a nutshell. Okay, so this is the powder with a high cohesive index, so difficult to spread. So here really important, we did the correlation between the GranuDrum instruments, so the rotating speed of the drum and the surface flow speed of the recoater. The experimental protocol of this study, we analyzed the flow behavior under different states. So the normal temperature and relative humidity. Then we heat the powder in the drum and measured it at 200 degrees for 2 hours. Then we did the same for the third powder, so at 200 degrees, and then we cooled that for 2 hours. And the fourth state is 200 degrees heated up for 2 hours, and then we cooled down the samples at room temperature for 1 hour. We did that only for sample A. So when we take a look at the results, the sample A is showing different behavior regarding the virgin powder and the processed powder. So the virgin sample has a probability to form agglomerate due to its fine particle, but with heat treatment, shifting behavior is happening, no humidity, and the chance to agglomerate will be negligible for the hot one. So here, when you can differentiate the first curve, you see the blue one is the virgin powder. So we observe a shear thickening behavior when you increase the speed. You have the cohesive index in the y-axis, the rotating speed at the x-axis. So the virgin powder will have a tendency to agglomerate, and it will be difficult to spread at high speed. When we take a look at the other curve, you see that the hot powder, after 2 hours at 200 degrees, has the lowest cohesive index, so it will be easier to spread and even easier to spread at high speed. And the two powders that were heated here at 200 degrees, then cooled down for 1 and 2 hours, gave a higher cohesive index, but still lower than the virgin one, because the tendency to catch humidity is increased than regarding the sample A. So then we observe the same behavior for the sample B. The shear thickening behavior for the virgin powder. So the cohesive index is increasing while the rotating speed is increasing. So the spreadability will be difficult at high speed. And we observe here a small shear thickening behavior for the hot powder. And then the cold powder, we observe a linear behavior. So the sample C, we observe a shear thickening behavior, but this is quite the same. So the rotating speed has no influence, no really big influence on the spreadability and on the cohesive index. And finally, the stainless steel, the results are quite close. So we observe here also a quite shear thickening behavior, but the curves are really close one to each other. So the summary, we observe here the cohesive index for the powders at when we take a look at the virgin sample, the sample A has the highest cohesive index compared to the other powders. Also, the cohesive index increases with the rotating speed. This trend is the same for the 4 virgin powders samples, but more dominant for the finest powders due to the highest possibility of van der Waals forces, which is obviously. So finest powders have more chance to form agglomerate. Regarding the process powders, especially for the sample A and B, the thermal stress completely changed the behavior with the modification from shear thinning to shear thickening. Globally, every powder achieved a better spreadability, so a lower cohesive index, when it was heated up and after cooling down. However, sample C and sample and stainless steel are not highly affected. So the conclusion on the spreadability, the cohesive index is higher at room temperature and humidity. The thermal stress induces a better spreadability, and it's really dependent on the PSD. So the second key parameter is the packing dynamic. This is the stage between the bulk and the tap density. It's how the powder will pack, and it's important for the parts porosity. So again, the assessment method we use is the GranuPack instrument. So the description of this instrument, we have a distance sensor. We'll measure, in fact, the density after each tap. The tap is 1 millimeter free fall. So for this instrument, we have an accuracy of 0.4% repeatability. We will see the evolution of the density. To show you again the video of device. So this is this box, which is closed for safety purpose. So we put an initialization tube. I will explain it later. We have an initialization protocol to erase, in fact, the user dependency. This is the cell we use. We need to pour roughly between 35 and 40 milliliter. And then the initialization tube goes down. So we pour the powder in the cell. Here, obviously, we had a small user dependency, but this user dependency will be erased when the tube will go up. So this is the initialization protocol. The tube will go up as we do comparative. As we did comparative measurement, the powder will aerate, and then the user dependency will be erased. After that, we will put a small piece of metal. This is our trick to increase, in fact, the accuracy of the sensor. This is a piece of metal, which has a small impact, in fact, on the bulk density, but as this is the same operator each time, with this impact. And then the sensor will go down without touching this small piece of metal. And then we start tapping. We do 500 taps, and after each tap, we measure the density. As you can see on the right, this is the software. We measure after each tap the density, and so you see all the packing dynamic of the powder. So the results you get, we get are the following. So you get the free bulk density, the tapped density, the NHAL parameter, which is really important in additive manufacturing, which is the number of taps to reach half of the variation of the density. well-known Hausner ratio, which is the final density divided by the bulk density. So the closest is the Hausner ratio to 1, the best will be the packing dynamic. Then some different parameters like the car index, the Pro infinite, and the toe index. So in this study, we analyzed the flow behavior under only 2 different states, so the normal temperature and relative humidity, and the hot powder heated up at 200 degrees for 2 hours. Regarding the aluminum alloys, we observed that the sample A virgin in blue has the lowest bulk density compared to the sample C virgin in green than the sample B virgin in red, which are close. But after 500 taps, we observe that the sample A has the highest the highest tap density compared to the 2 others. After the heat treatment, the sample B, the sample A has the highest tap density than the B than the C. When we take a look at the stainless steel, we observe that the virgin one has a lower bulk and tap density than the heated one. So here, this is a summary of what we saw and also the comparison between the Hausner ratio. So you see sample A virgin and sample A after 2 hours heated up, sample B the same, sample C, and stainless steel. So if the powder is heated up, the Hausner ratio decreases. As we can see here, the Hausner ratio is in blue, except for the A, because as you can see here, the error bars are too high. So when we take a look at the sample B, C, and stainless steel, we observe that the Hausner ratio is decreasing. And this is the similarly trend for the tree and taps bulk density. They are increasing after heating the powder. So the Hausner ratio is decreasing, which is better for the AM process. The conclusion on the packing dynamic, is higher at high temperature. The Hausner ratio decreases with thermal stress, which is better for the additive manufacturing process, and the thermal degradation is beneficial for the process. So then we took a look at the electrostatic charge. So inside the powder, there is a flow between the particles, but also between the particles and the material, and it induces the cohesive forces. So I explain again the instrument description. So here we have a box, we have a V-tube in stainless steel, and we have a Faraday cup to measure, in fact, the charge. Precision of this device is roughly plus and minus 0.5 nanocoulomb. Again, the video of the device is going to be easier to understand what we did in the study. So here you have the charge, and then we have a Faraday cup. We measure, in fact, the initial charge in the powder, because due to shipping, storage, and so on, you might have some initial charge in the powder. So here in the software, you can see, we measure the time and the charge. When we reach the plateau value, this is the initial charge. Then we pour the powder in the feeder. We close the door because you can control the humidity in and we start the flow. The powder will acquire some charge between particles and particles, but also between particles and the pipes. And then you get at the end the same plateau value. This is the final charge after the flow through the pipes. So to summarize quickly what I said, we measure the initial charge, the final charge, and we have the process charge. So the experimental protocol again, the electrostatic charge were measured against stainless steel 316L pipes, virgin powders and powders after heat treatment at 200 degrees. And the the experimental was done at room temperature and relative humidity. So first, regarding the sample A on the left, the virgin sample A on the left, it's impossible to conclude due to error bars. Stainless steel has the lowest amount of charge. It might be due to its highest PSD. After a flow through the pipes, the sample A acquires a lowest amount of charge in comparison with B and C. And after the thermal stress of 200 degrees, the powder behavior is highly interesting. In fact. For example, A and B, initial charge decreases, and the final charge change from negative to positive. For example, C, the trend is conserved, stainless steel is slightly impacted and become positive. So the conclusion on the electrostatic charge, the virgin powders sample A, B, and C negative amount of charge. The stainless steel acquires quite zero amount of charge because it's against stainless steel. So the electrostatic charge, the behavior is highly interesting and change after the thermal stress. So again, the general conclusion you saw before, working at high temperature improve the spreadability, working at high temperature improve the packing dynamics, and the thermal stress has a big influence on the electrostatics. So the contact forces need to be assessed for the cohesion, but also the electrostatic to have the whole picture. You need, in fact, to correlate the measurement cell and what's happening in the process. And so those are the general conclusions today. Okay, this is the end of my presentation. If you have any questions, I will let Tiffany know.
Yeah, thank you, Martin. That was very informative. We would like to open it up for some Q&As. So if you guys have any questions that are currently on the line, please send them through the Q&A box again at the lower right-hand section of your screen. And I don't see any just yet, so I'll go ahead and get us started. So first question I have is, which characteristics are really important for BPF and binder jet processes in terms of powder properties?
Yes, okay. So I think for powder bed fusion, you need to be able to evaluate well the spreadability in order to have the perfect powder bed, in fact. It is always problematic to stop the process when you find the powder bed isn't flat. And then in binder jetting, the key is to have, I would say, a build not too packed, but not too loose, so you can easily pour your binder in. So for us, we think it's mandatory to know where you are in the packing of your powder. So the Hoffman ratio is important, but moreover, is the way your powder will pack and how fast it will pack. So if you can mimic what's happening in your process by measuring before putting the powder in your machine, we think that's a win, in fact.
Thank you. I do have another question. So back on slide 18, would you be able to give us some advice for that powder?
Okay, I will go back to the slide. This one. Okay, so I mean, it all depends if you want to have the best productivity or not. If you want to print fast, so work with the highest recorder speed, you will need to use a hard powder, so the cohesion will be low at high speed, so the cohesive forces will be low, so you can spread at high speed. But if your purpose is to find a sweet spot where the recorder can spread the same way all the powders, then you have to work at low speed, in fact. So the powders are quite behave the same. So this sweet spot is important if you recycle the powders also.
Wonderful. All right, my last question here is, based on your experience, which parameter will influence the behavior of the powder in the machine?
Okay, only if based on our experience, so the macroscopic properties, so only regarding the macroscopic properties, the humidity will play a big role. The way the powder is stored and handled also. So this is what we hear a lot for the moment in the whole supply chain, from the powder producer to the final user. And by humidity, we talk about also electrostatic, because those are closely related and at the moment not really understood. It is going to be a big challenge, we think, for the upcoming year in terms of powders.
All right, thank you. Well, Martin, that's all the questions that I have from my end. I will ask if you could just flip back to your last slide there so we could put your contact information up again. And we'll just wait here a couple seconds, see if any other questions come through. Okay, I don't see any other questions coming through, so we're going to go ahead and wrap things up. But again, for those of you still on the line, if you think of some questions later on and you'd like to reach out to Martin, his email address is available as well as his telephone number. In another day or two, this webinar recording will be available on the America Makes YouTube page. So in case you don't jot it down now, you'll have another opportunity here shortly. But Martin, I do thank you for taking the time to prepare this webinar for our folks today. I hope that everybody enjoyed it, and I hope to have you back soon.
Yeah, thank you too. Thank you.
All right. Thank you. Take care. Bye.